I'm the only guy who don't receive many students in this semester. I just get 2 students.
I had 3 within my.
I have one permanent student from PNC.
that,
That
yeah.
Last Wednesday, I had 3 people, and like it was almost like it was planned because after I helped the one person
Yeah.
and they left, the other one came in right after them, and then like after I helped them,
Yeah.
you know, like pretty fast,
Yeah.
and they left, another one came like in like a minute later. I'm like,
Yeah.
is this just like scheduled like to
Yeah.
like?
one day I got to fight together. And Thursday, I will be alone there.
Yeah.
No other two with me. It was like,
I thought it was like yeah.
oh,
Homework 3 is this chapter. I think probably this week we will finish.
Chapter 3rd.
Chapter 3, yes. This chapter.
Yeah.
We will skip up. Introduce Kate. Introduce Kate. Just remind what we discussed last time, so we can continue.
He's taking her.
Okay, that is what I think in last class we discussed for the Kepler's problem is I think only he recognizes. For the Kepler's problem that we consider both is the inverse square law, right? And for that case, we can obtain this orbital equation for r as function theta. Then with this one, we have two constants. We introduce p is this L square. L is angular momentum, right? Over mk. K is this coefficient. Then E is introduced eccentricity, right? So that is this control by this energy, angular momentum, and this constant here. Then we can discuss depending on energy positive, 0, and negative, and the minimum of V prime. This value is from the larger than 1 equal to 1 and less than 1 and equal to 0, right? So that is open orbit and closed orbit. Then we come focus on this ellipse for the this E is less than 1. And in that case, we have, if you remember, we have this R minimum, this and this one, this R maximum, right? Two turning point. Then this minimum, maximum is controlled by these numbers. Here we have this P, right? And of course, it's also depend on this the semi-major axis A. Sorry. So the energy has relation with A. That also gives us information about how the shape of the ellipse depend on the initial energy, right? So that we discussed. Then with introduce A, we can have rewrite the P and the R minimum as maximum as well as the output equation in terms of A. So we have this formula. Now next, or today's question, we will ask ourselves. Okay, the first one, the velocity, right? How to determine velocity and actually, to this is radial velocity is R dot, right? And the angular velocities are theta dot. And the V in terms of theta. So that is, if we know the orbit, how to express the velocity. So that is our first question here. We are going to discuss. Second one, then we are going to ask ourselves what is the period. And if in the, how about this function of R, and, sorry, R as function time, and theta as a function time. For this, we will consider either this case, there's a parabola, right, when energy equal to 0, and ellipse. Okay, so I hope this we can finish, and then if at the end if we have time, we can introduce another conservation quantity. We know the angular momentum is conserved. So we will see or introduce another one. So now let's first discuss those, right? And remember this one, the relation between this. If we know V R V theta, so that is V R squared plus V theta squared, right? So that is, and then this one. Okay. Now let's first discuss there are two ways. Okay. Then I think this, let's discuss first one is R dot. To get R dot. Okay. And first R dot. There are two ways to get R dot, but let me give you this R dot. Is first from the energy conservation. If you remember, energy conserved, and we know energy is half of m r dot square, and plus the radial part, and the minus potential, right? Okay. And so from here we can get r dot square. You just move this to the left hand side. The r dot square is 2 over m. Here we have a 2 over m, right? And inside the energy minus this L square over 2 m r square plus here, right? K over r. Then we use this relation. Energy replaced by the minus K over 2a. So you have this minus. I give that minus, keep this, okay, let's keep it minus K a minus L square m 2m r square plus K r. Then the, now we are going to use this one. Since here is r, right, we are going to find this one in terms of theta, right? That is our goal. So now this is still r here. We have r, but we are going to use this one. So now let's keep continue. 2 over m inside minus k over 2a. That is still here. Now this one is minus L square over 2m, and r square is here, right? So now we have. Oh, okay. Let's still keep r. then later we're going to, so okay, we're going to use this one here. Even remember this one, right? Oh, L square over mk is this one. So here we have L square, and then we have multiply k, right? So that one, this constant we're going to replace by k a 1 minus e square, because that is lambda e square here, right? And divided 2r square minus k over r. I do this one because the homework, one of homework, this one, we are going to use that formula, so I just give you the first, this one. And, okay, wait a moment. Yeah, then we take this, r square outside, and we also take k outside, so we have k m and a outside, so m a r square. And inside, you will see it is very easy, so just give you a final result. A square, e square, minus r square. So that is one, that is in terms of r, right? In terms of r. Now we keep going. So we are going to find in terms of theta, we can do this way. Because you can also go further to substitute this one into here. That is another way, but we can also find another. Okay. Yeah, okay, here. R dot, right? R dot is dr d theta dt. Can I write this way, right? So now this is a dr d theta dot, right? Then dr d theta, now I have this function r as a function theta, so I can do the derivative very easily. So I just give you a result is, okay, so I have dr d theta, r dr d theta is this one, r e sine theta minus theta prime divided by 1 plus e cosine theta minus theta prime, because you just do this, so you can see that. So I'm going to say here theta dot, and that is r theta dot is this one, right? So in terms, that's first in terms of this v theta, then we are going to see theta dot, we put it. So e sine theta minus theta prime, 1 plus e cosine theta minus theta prime is theta. Let's say this equation 1. Okay, and now equation 2, so now let's look at the theta dot. If you remember, theta dot is L over mr square. Okay, so the v theta square is r square theta dot square, so we just substitute this into here, and also r square this one. So we just substitute into this, we will have, and just give you this, r square, L square, m square, r to the 4th power, right? Okay, and then we are going to, this will cancel the r square, so we have only one r square. Substitute this one here. So we have k square over L square, 1 plus e cosine theta minus theta prime square. Okay, so that is theta square. Then we have, if you use a this is the, okay, whatever I use the, so now we look this v. V is v square is v r square plus v theta square. Now v r square is here, right? So v r is here. So we take the square. That is okay. So we have, okay, since we are first, so this one we are here, right? So that is E sine theta minus theta prime, 1 over plus E cosine theta minus theta prime, square, A theta square plus A theta square, right? So this is 1, then you just move together. Then finally we will have is 1 plus E square plus 2 cosine and 2 E cosine. Just extend this one. Here. This square can be became is take this okay, let me give you keep it here. Is 2 E cosine theta minus theta prime and denominator 1 plus E cosine theta minus theta prime square. Now we can substitute this square here. So here let me do that. We see that square is here, then you can see the term cancel right here. This is a 1, this is also. Then finally this became simple is K square over L square 1 plus E square plus 2 cosine theta minus theta prime. That is equation 2. That is V squared, then you take square root is V, right? So we answer this one and this one. This one also have here, right? This one is supported. This is equation 2, and this is 3. So we have this. Now, but equation 1, when we have equation 2, you substitute equation 2 to equation 1 can be VR. We can also have, right? That is. So when you take square root, that is square, this is a cancel because we see that it comes to here, so that is cancelled. Then you have only L over K, K over L and multiply this one, that is the R, right? And so I just save time, so I just leave here. Then we have to, now we are going to answer this question about tau, the period. What is the period and how to find this orbital R, or R is function time and theta is function time. This is a challenge. So now first, to obtain this one, there are 2 formulas we can have, right? Remember we have R dot, which is 2 over M energy minus V, that's general, right? This formula is square over 2M R square from here. So we have T is the integral from R naught to R and dr square root 2 over M E minus V minus L square over 2M R square. So you can see here, if we can do the integral, then we can find time. Then we are going to start if we take this circle. This is a close from the take the one circle, so that's we give us time from R naught to back, right? So that is a general formula. Now let's consider. Let me give another formula here. This is a 1. Another theta dot, right? Theta dot is equal to M R squared over L. So from here, we can also have another formula. T is in terms of theta. And d theta, M R squared d theta over L, right? If this equation, I'm going to see another question, topic, so I name this equation 1 and 2. Now, which one is better? Either this one or this one. So we are going to discuss in case, which case is better. Now first, let's use the R. This is, we have this R orbital formula. Since here we need R, right? This one also, but if we put here, that's function theta. So that's a bit, if we use this one, we substitute R in terms of theta, then we can do this one. Here is only for R. So both are difficult. But let's see which case is possible. Let's first use this formula. 1 plus E cosine theta minus theta prime. That is 1. And the V is minus K over R, right? Because we use these two, then we are going to substitute. So this one, first one, equation 2. So equation 2 is reduced to T equal to theta naught to theta. And I'm going to make this constant outside, so let's take on constant outside. L, here L square, right? And L square, okay, because this is square, right? So that is to take square as a false power. Then we have this one, so this L cube. Then that that's M square, but we have this is M square, and we have M, so that is over M. And the K square here is square. So then this one inside, right? So that is theta naught to theta. Is theta 1 plus E cosine theta minus theta prime. Is this formula. But even for this formula, because this we have an E here, it is not easy, right? In general, it's difficult. Even though we have this orbital, this one, if we substitute here, it is, for general case, also complicated, but later we are going to discuss. We are going to introduce another variable, and we can do that. But let's look this one. So if we consider this one is difficult, then only when the E equal to 1. So E equal to 1, 1 minus cosine, 1 plus cosine, that is doable. We can, at least we can do the integral, right? And if you know that is correspond, energy equal to 0, it's parabola. It is a limit, parabola. It is a limit of the ellipse, right? When this A increase. So the energy here, energy go to 0, right? So A is equal to infinity. Let's look that limit. This one we can do. So now, let's first work on this. That is this case, right? We are going to answer these 3 questions for a case. E equals 1. Then we go to the ellipse. Okay, so if equal to 1,
Is
Yeah.
that theta dot and that theta dot are same or different? L over m square. And
this is a square, right?
This theta dot equal to L over m square,
That
and that right
you
side
take the
here.
reciprocal.
Theta dot third step. Right side, third step. Theta dot equal to m square. Above
This one, right?
Yeah.
Oh, sorry, I just made a mistake. It's the inverse, right? Yes, that is inverse. And then go to here, that's correct.
Yeah.
L, M, R, yeah. And the d theta, yeah, so that goes, yes, that's correct, right? Okay, thank you. So now, let's consider only when E equal to 1. Then this integral T even there, right? First T is equal to L Q and MK square from, let's see, still use theta naught, theta, and, okay, now we have d theta, 1 plus cosine. Okay, now to make the integral also simple, so we select theta prime equal to 0 case, right? Theta prime is any arbitrary initial angle, let's select 0, means we are going to, we are going to, if this is our minimum, we are going to select this here, at this position, theta 0, theta prime 0, and theta, this is the theta, right? So that is what we do, so make this integral simple. Otherwise, you can also find, because you can take the theta minus theta prime is equal to theta, another theta, right? Then the d theta minus theta prime is equal to d theta, right? So that is not big deal. So now look this one. For this one, the integral, yes, okay. Then we just simply max, right? This one, 1 plus cosine theta squared is half theta square, half cosine theta, right? So this one is became, let me see here, okay. D theta, I have a factor, okay, yes, factor 4 cosine to the 4th power. Right, from here to here, that makes sense, right? Okay, so I just go. Then in this case, or just take this factor 4 outside, and k squared L to the Q. Now this one, cosine inverse is a second, right? Then the remaining part we just define, for example, we can define, and the intermediate variable x is tangent half theta, then dx is second square half theta, d half theta. Then we can, you know this is correspond to this also, because we did define this one, then let's back again, and k square. Here I need a factor 2 here, so I have observed 1 factor 2 over there, so I have a 2 factor here. This 4 give 1 here, right? Then that is this one, and the inside is second square half theta and d tangent, right? dx half theta. Then you know is this one is also theta naught theta, theta. This term is 1 plus tangent square half theta. Then we can do the integral, right? So now let's get the final result is keep this constant outside. Then we have this one is tangent theta, another is tangent q, right? So that is tangent half theta plus 3 over tangent q half theta, and then just from theta naught to theta. Clear this blackboard. What is the equation here? T here, so that is a function of theta, right? So now we have we can write in terms of this one. 3 tangent half theta. I just mark 3 both sides and move all together in the same side. Minus 6t mk squared over L to Q equal to 0. Of course, in this case, it is not easy. It is like a translator function to solve this theta function. So this is a kind of equation, right? Like here, if it's, we already defined x, right? Something like 3x plus x cubed equal to constant c. If I move to this constant c, is this constant multiplied t, right? So you are going to solve this one and find x as function time. Solve this transcendental function, usually you need a numerical or write small program to try to find in which t the x and you find all the x as this one, you have to wait finally. So in principle you can do that, but it is still not the direct formula here. So what is x? X is a tangent theta, right? So that means give in principle theta as function time. In principle we can do, but it is not still not the direct solution. We cannot. We have to solve this equation, but if you know this transcendental how to solve it, right? You have one curve this is a linear, another cube, and there's a cross point. Because that cross point t is the solution of this. So this is a x, right? X as a function. This is a x linear, and you have x cubed. So that is one of the solutions for this. Of course, this is 3x, for example. This is x cubed. When this plus this is equal to this ct, then that is, so you are going to find this one, and then maybe have some others point. So that is example give you how to solve this transcendental equation. So once we have that, in principle, R is L squared over mk 1 over E. E in this case is 1, right? So that is just in this case cosine theta as a function time, right? If we know, suppose we know, so in principle we can alter this. But again, as I said, it is not straightforward. So but at least we have the equation, right? So that is at least for this case is doable, not like integral here. We at least give us the solution or equation for the solution. So that is the answer of this one, and t. T here, right? This t. If you take this 0, this 2 pi, you can get the t. That is the top, right? So that is this case. Now we consider the second case. So that is case for this case. Now this is really close to this. How about this case? In this case, see we have two formulas, right? In this case, since we have an e here, it is not easy for us to integrate. So we give up to start from consider this formula. We are going to consider this equation and see we can. So for this case, we are going to use t is from r naught to r dr and square root 2 over m. Energy in this case we have this we have already minus k over 2, right? Let's write up here, and then we are going to say e minus v and minus m squared over 2 m squared. We are going to work from here. And you say here is not easy, but for this case, we have a technique. Of course, this technique is the previous or the famous Kepler. They are 250 years ago, right? So they work on this, and so we have this how to solve this. So now we are going to solve this. To do this, first we are going to introduce a new variable, which is very important. So now let's consider the ellipse here. This is okay. So suppose this is here, this is focus here, and we have R. This is R, this is theta, right? And here, this is called the P point. And now, he introduced a way that we have A, right? I just say A, right? So that is A. So with this A, we keep this A plot is the circle. It's not like circle. So introduce the circle, which is a radial is A, is semi major, okay, and then not good. But the key is here. So what happened is here, introduce another, we have the same x. This vertical, so we have another point, P prime, on this circle. Then we have from P prime, since this is A, right? This is A. So we introduce a new angle here. Here's a phi. Psi. So we introduce psi is an auxiliary variable. Auxiliary variable. And this variable is angle, right? So why we introduce this, and you will see when we introduce this, it will become easier to get this result. Now when we introduce, we first want to analyze the relation between, this is EA, right? Between A, theta R, and this, okay. This is X, right? X, Y. This is Y. So let's first, the cosine psi. Cosine psi is X, this is X, right? Over A, right? So from here we have the relation X is function A cosine psi. And once we introduce this one, okay, I think I start a new topic for this one, so I'm going to get another equation one here. That is introduced. Then you may say why? Okay. Now next one is you will find here R squared. Geometrically, right? R squared. This is R squared, right? R squared is this is Y squared. And this is this EA minus X, this part square, right? So that means EA minus X squared plus Y squared. Geometrically, just find R, and then we're going to discuss. So X here, but now what is Y, right? Y we're going to find, we are going to eliminate the X and Y, but in terms of A and other parameters. So that is, if they say this equation 2, then now equation 3 is because there's an ellipse, right? For the ellipse formula here, mathematically we know that is this. Then we can substitute X to here. So equation 1, if we say this is 3, go to 3, then you have this A squared cosine squared psi over A squared, so then this A cancel plus Y squared B squared equal to 1. Then from here we can get Y or Y squared. for the y square, I think this is also very simple. You can do yourself. Let me give you the result. And we have y square is b square sine square of psi, right? We just do this. Move this to left hand side, or move this to left hand side. 1 minus cosine square is sine square, right? So that is very simple. Then if this is equation 4, so equation 4 go to equation 2. Okay, so now we go back to r square is here a EA, right? So EA minus x is a cosine psi square plus b square sine square psi. And all right, there's another relation between this e square is 1 minus b square a square. So that also because b square is a square 1 minus b square. This is equation 5. Now we have a 5 go to here. Again, this is equation 2. Or 2 prime, let's say it's 2 prime. Then we have r square. Substitute is here. Then manipulate this formula here. Finally, we have the r square is very simple. A square 1 minus cosine psi square. So r is a 1 minus, sorry, there's an e. E cosine psi. Equation 6. So now, if we introduce psi, r is optimal equation. Another previous r equation is here, right? That in terms theta. So now we can also have another formula in terms psi. When psi we introduce it here. So this angle is this variable is very helpful. You will see later we are going to find r as function time and theta as function time. If we introduce psi, this integral it becomes simple. Okay, so that is our next job. Here, I know there are some of the formula here. If you try to familiarize this from the mathematics for the ellipse, and this relation y is equal to EA, this from the focus to the origin. That is also the basic mathematics, so I just skip that. Now, we're going to come back to integral time, right? We are going to find this time over period, then as well as the general time dependent of r and theta. So with this, then we can have the t. Let's go back to come to here. T from still from the beginning r function r and 2 over m. Now I'm going to substitute e. This e is k minus k over 2a, and v is minus k over r, so plus k over r minus L squared over 2m r squared, right? Now I'm going to substitute 6 into this formula here. Before that, we can also rewrite this one. If I multiply k and this is mk, L squared over mk is p, which is a multiplied 1 minus e squared. So now I'll do again before we substitute that one. So we have take this constant outside. So that is m over 2, right? Take this m over 2, r naught to r, b r. Okay, I'll also take the k outside. K outside, so we have inside is r minus a, 1 minus e squared, over 2 plus minus r square over 2a. Here, this R. So I take the r square outside, then they go to the numerator, right? This r square. Then here, this term you have r square, this one. K take outside. Then this one became r. This one is this term, this become constant. Okay, up to now we can substitute this. So with this, now before the substitute, we are going to find the relation between r naught r and the angle of psi, right? So we take the r naught. If r naught, if we select r naught is r minimum, and what is r minimum? R minimum is here, right? But this turning point, so psi is 0, right? The angle is 0, theta is also 0. So in this case, we have psi now is 0, correspond to this, right? And for this also for t equal to 0 case. So suppose we have select t equal to 0 case, it corresponds to r just at the turning point with the minimum, then that angle is 0, right? So t is from, okay, constant, constant I have m over 2k. All right, so then this is from 0 to any angle, right? R naught to r, that means from 0 to any angle psi, then inside here, r, right? R is a 1 minus e cosine psi, and dr, you just do dr here, you see that you have a sine, right? So that is a e sine e sine. Right? This is when you do the dr, then you have a negative sign, right? AE, I think a negative sign. Did I move somewhere negative sign? Oh, yeah, cosine is a negative, so it's a sign, yes, that is. And denominator, here we have this a 1 minus cosine psi, this r, and this constant a 1 minus e squared over 2. And this one is square, right? So that is a square 1 minus cosine psi square over 2a. Then what we need to organize, and some terms you can cancel. So finally it's very simple. Just try to manipulate these terms. Then finally we have square root. We have a square, and if it comes to here, it's a to the fourth power. We have 1, so a to the cube, right? And the k here, factor 2, we have also this one is cancelled. And from 0 sine, the inside is only 1 minus e cosine sine e sine. See, even though the intermediate is very complicated, it looks complicated, but it's very doable if we introduce this auxiliary variable psi. So now this integral is very easy to do. Now we can calculate the result. It is m n to the k, and psi, this is psi, oh okay, sorry. Yeah, that's integral. Psi, and the plus, right? A minus, because sine and cosine, so minus e sine psi from 0 to any angle. That is time. And we can easily get this period. If the time, one period is the angle of psi from 0 to 2 pi, right? One period. So with this formula, if we have this, this is a formula. Let's keep here. 7, right? Okay. So now we can discuss period first. Then we discuss the general. So for period, tau equal to how much is t from, just immediately, tau is m a to the q over k minus E psi from 0 to 2 pi, right? Let me just substitute this. We know that is 0, right? 2 pi is 0, 0, 0, so only this term. And that is 2 pi. So that is 2 pi. To obtain. So, and this is a famous third law of Kepler's third law. So we have, he used the square, right? It's 4 pi squared m a to the q minus k. That is proportional to the a q. What is k? Remember, k is dependent on the initial energy. And the initial energy gives us the shape of the orbit. So what he observed, so this is a famous, the third Kepler's law. That is a famous, his observation that the period square is always proportional to the a to the q, and a is major semi-major axis. So that means if a increased, the orbital more became a more compressed like this, right? So that the time period is also increased. There's another term I think I can speak that. Yeah. Okay, so then we first answer this question. In this case, we can get very easily the period. If we have E equal to 1, we can only have the transcendental equation. Then we are going to solve the transcendental equation. That is, again, not favorable, but this one is formula. Now, so this is tau, but now next time, the next job is we are going to find this one. Okay, this is our question. How to do this? Now we can do this, consider this. Start from here. So from equation 7, we know T. Let's introduce omega. Okay, before that. Introduce omega. Since we have a tau, so we know the omega is has a relation with tau, right? 2 pi over tau. That is omega. Then here tau is this formula here, so that is equal to k over m a to the p. So if we introduce this, then you can see here, this is tau omega, right? So the equation we can rewrite is omega t, left hand side, is equal to this. This, when we set to 0, this is 0, this is 0, right? So that is only the function of, yes, function omega t is psi minus e psi. This is a very important equation, and from here, in principle, we can find psi as a function of time, right? You just take inverse. Now the time is function of psi, then in principle, we can get this one. Then the next one is we're going to find these two, right? If we know psi, can we do that? It is, the answer is yes. So first one, and from here, in principle, then the R is A 1 minus E 1 plus E cosine sine t. If we know that, then that gives us that's function. So this answer. Now the next one is we are going to see how to find theta. So in order to find theta, we first know this relation between theta and psi. We know the relation between R and psi is formula. What is the relation between the theta and psi? So now we are going to find this relation here. Okay, from here. So now, because cosine sine is x over a, right? And you erase. You can remember x is a e plus r cosine theta. over A. Then here we will have R. Since R is a function of theta, right? Now we can substitute function of theta to this one. So that is okay. Is here. There it is. Is A? This A is already here. The first term is E, right? The second is R. Okay. R, A over R cosine, and then this is E plus A over 1 R. R is A 1 plus E cosine psi. So then the organizer moved its cosine psi in the left hand side, cosine theta is right hand side. So now finally we have this cosine psi is E plus cosine theta and 1 minus E cosine theta. I think somewhere I have the sign. I think that is is minus, right? That is minus. Let's see. Yeah. Minus. That's right. Okay, so now we have this formula. Now if we say that this equation is 9, that is relation between cosine theta, cosine sine cosine theta. So in principle, if we know the angle of psi as a function of time, then we can find this relation or the theta as a function of time. This one you can do by substitute this one into here. But we can also manipulate this one in the other way to make this simple. So now let's see, from here, from 9, we can also get the cosine theta is a function of cosine psi minus E, 1 minus E cosine psi. And then we have 1 plus cosine theta divided 1 minus 1 minus in the numerator, and that is a tangent, right? Cosine theta. That's be equal to the right hand side 1 minus cosine psi minus E, 1 minus E cosine psi, and then it's 1 plus cosine psi minus E, 1 minus E cosine psi. That gave us 1 minus cosine psi 1 plus E, and 1 plus cosine psi 1 minus E. So let's look at the left hand side. Left hand side, we know that is very simple, the tangent square half, right? Left hand side, 1 minus cosine theta, 1 plus cosine theta. That is half. The numerator is half of twice the half of sine half theta. The denominator is 2 times of cosine half square half theta, right? That is. Then that is tangent square half theta. Then we see the right hand side. Similar things. This is 1 minus cosine psi divided by 1 plus cosine psi. So that is also tangent. This 1 plus e divided by 1 minus e, so that is tangent square half sine multiply this factor. So finally we have tangent half theta is tangent half sine and square root 1 plus e 1 minus e. So t, right? So that means in principle the theta as a function time is doable. If we know the function time, the psi as a function time, we can do it. Okay, good. Okay, we now come to discuss another factor. Again, if we want to inverse from the angle tangent and theta to theta as a function time, you also take this inverse, right? Tangent inverse. That is doable. If you familiar with a code, very small code you can write, and you can finally find the curve. You plot the curve, and you can analyze fitting the curve. Then you got this either polynomial behavior or use a polynomial to fit, or whatever. You can find this behavior curve by your knowledge of mathematics. So I think up to here we answer the question first. What is time period? Tau, right? So we have a tau, and then how to find the r as function time and theta as function time. If we know this, and this one is by solve this equation, right? But this one is still a sinusoidal, a transcendental function. I didn't write down here. This is again transcendental equation. So to solve this means how to find the relation between psi and t. You need also plot and find the cross point and get this. So in any case, we have to use this transcendental equation. Now the last one we are going to, before we discuss scattering, which energy is positive. So far we focus on the closed orbit, right? So energy is negative. Then the behavior we know is also almost like a closed orbit, the motion like this. Now for this closed orbit, we have another addition. Additional conservation or conserved vector. What we know is angular momentum is conserved, right? Total energy is conserved. That we already beginning to discuss this central force problem, right? In general, any force, any type of central force, and we always get this. So now we are going to discuss for this Kepler's formula of a force, which is inverse square root. In addition to this, we will have another one. So which is a new one? Let's follow the idea is look this one. Look the time derivative of P with a linear momentum, right? Cross product with L. Let's look this term first. So this one, we did do the time derivative for this one and then do this one, right? So that is dP dt cross L plus P cross dL dt, right? Then this one, since angular momentum is conserved, so second term is 0. Then that is the only first term I'm going to use P dot cross L. That means this cross product, we do not know what it, but it is a vector. So this vector total time derivative is equal to the cross product of linear momentum, time derivative of linear momentum is angular momentum. Now we are going to look this one. So what is this one? That is dP dt, which is Newton's second law is force, right? And this force we consider the central force, right? So that is, central force is a function of r with the along the radius, right? Along the r direction. So that is this. Okay, so because then we have this one, so then there's a d dt p cross L is equal to, I'm going to substitute this into here, so that is f r over r cross this L, right? And what is L? Okay. So f r over let's see, r over r cross L is r cross p, right? R cross p. P is m r dot, right? This is L. So now you can see here we have three vectors cross products. So which one, if you remember, so the cross product, the three vectors, we can rewrite is equal to A plus B plus C is equal to first B A dot C minus C A dot B, right? Remember this? So now I'm going to direct to write down here. This is a numbers, right? This is not vectors. I keep here. If I say this is A, let me see if I use A is R. So now I keep this one outside. Inside, this is A, B, C, right? So that is B. B is still R, right? B is the B. This is A, and this is a C, right? I will take, let me see, I take M also outside, so M here. Okay. Then inside B is R, and A is R dot right? C minus C R dot and R A and B. Okay. Here, this is a inner product, so that is R squared, right? And this one, I think, let's first keep this. Okay, let me keep it, and then I'm going to manipulate. So now F R over R, as we keep here. F R, okay, so inside R here is, okay. I think now I need it. So let's use this one. If we consider D, R, dt, the inner product of R is R dot R plus R dot, right? It's twice of R dot, right? And this one, R dot, okay. And this one is equal to dr squared dt, right? And that is 2r dot. This is the numbers. This is the inner product, right? So you see this inner product here, I can replace by this. So let's keep continue here. So now here I have M, F, R inside. This is R vector. This vector still keep here. But this one is this. I have a 2. Oh, wait a minute. Yeah, this is twice of this, right? So equal to 2 cancel, right? So that one, that's equal to this. Yeah, so that is R dot, right? Minus R dot R squared. Yes. Okay. So So in this case, now I'm going to do this way. I take r squared outside, and this inside. So you see this one cancel, right? If I take outside, then here I have, because this, so I have r dot 1 over, this is a vector right here. So this r dot have a 1r, and then this one is cancelled, but I take this one, they have a r, 1 over r squared. So that is m f, I also take minus sign outside, so, okay. Take minus, then this term part, and this to the second, right? Minus m f r squared. And inside, this one first term, right? Take the r squared, take outside, so we have 1 over r dot 1 over r, and the second term is r dot r over r squared. And this one, write down first term, hopefully you accept as d dt r r. Right? If I do the derivative of r vector divided by r, I do the first keep this one, so that is first term. And then I do the keep this one as second. So when we do this one, we have a minus r squared, and then I have a r dot multiply this one, right? From here to here is equivalent. Then you can see here is total time derivative. That is the left hand side we have term, and then we have this also total time derivative, so I put it together. Okay. Alright, so maybe I use this false. Now we are going to use false is equal to this, let me keep minus m. So false is minus, just this Kepler's problem. Inverse square, right? So that r squared d t r. Then r squared also cancel. And minus the vector plus k d t r. Simply is a total time derivative. Or you can just move this inside. So now, that is left hand side is total time derivative. Right hand side is also said put together as a total time derivative of p cross l. That one minus this one, right? Minus mkr over r equal to 0. Right? So when we start from here, the goal is we try to find another time independent or conservation vector, and this vector is here. The new vector, I'm going to use A, which is A equal to the cross product of linear momentum with angular momentum and subtract this R, it is constant. So this one is Laplace Eugen Lenz vector. If it is a constant, means this vector direction and the magnitude always keep the same. Did I solve the time? Okay, great. So now let's try to have the visualize what kind this vector, what looks like, and when it is equal to constant. We can plot. This is a consider the orbit. This ellipse, right? So now let's consider ellipse again. Okay, so that is the focus here, and now at any point, right? So now suppose at any point here, this is R. At this point, this vector is this one substitute to this one, right? So now here, this is a P, right? P is a tangent. moment, linear moment always tangent with this P. Where is L? Perpendicular to the plane, right? So you see P, okay. Yeah. PL, right? So L is perpendicular, so P is this one, L. And give us P cross L is this direction. Then where is this term? This term is along this M, K, R, actually it's just R hat, right? Magnitude is MK. So then you will have the direction of this vector summation subtract, right? That is, yeah, okay. That is this. That is A. So that A, if the magnitude here and the direction is that in any case, this will always point to this direction and make the same magnitude, right? Suppose here, let me close at this position. At this position P here, right? And the P L, and that is give us to this direction. So that this one is P cross L. And R, this is R, right? So R is, okay, I hope it is M, K, R over R. Then you can see here, that is A. And you see this one, same, right? And I'll give you another example here. So P, in this case, P, right? P, and this P cross is this direction. P cross L. And R. R in this case is another M, K, R, R. Then the A is this one. So that is interesting, means implied for this inverse square law. There's another vector which is always keep conserved. And this vector is just defined like this. Okay, I think just time we finish this the closed orbit discussion. So on Thursday we are going to discuss is open orbit. One of the example is scattering, right? So we are working on how to discuss scattering, what kind of motion looks like. Okay, the homework I'm also will post on the Blackboard, so you have more detailed information about this homework 3. I go a little bit quick. So I thought almost to the end of October. Yeah, you can come in. And we have only 1 month, November, we need the chapter 8, chapter 9, and at least go to some of chapter 10. That is very important for the Hamiltonian, so I skip a lot, but I hope your intermediate step you can work on yourself, and if you have any question. Thank you. Thank you. So.
Thank you.
That's right.
Yeah, don't worry. This weekend's gonna be nothing but exciting. This weekend's just gonna be
What's going on, good?
It's alright, right?
Just this easy stuff.
Oh. I don't know, you tell me.
Sure.
I have to look
Just
at
get
it.
a little abstract.
I'll tell you if it's easier now after I get back over it.
Yeah. Change your perspective.
It's so cold that it's making me tired.
Yeah. It's ridiculous. Like hibernation.
Yeah, yeah.
Like, oh, maybe it'll be warmer when I wake up.
I try to remember your name is
Jemaya.
Jemai, yeah. Because you look like another is Zion. not Simon. You know Simon? Maybe 2 years or maybe 3 years ago, and he moved to the speed school. I thought, oh, you come back? So sorry, too many names I need to remember who is who.
It's funny, we look alike and our names sound alike.
Jemayan?
Jemiah.
Jemiah.
Jemiah,
Oh, okay.
yeah.
Okay. I've never heard
He's
that.
my evil twin. He came to school first.